Hello everyone. Uh, Let me continue the discussion on bending moment and shear force diagrams. I have told I have discussed few problems and I feel now that I don't have much to teach. Uh, So except that is with that intention I have taken one problem where I have something. So in this problem I have a UVL, uniformly varying load, or what is called as triangular load, and I have something to demonstrate. And in all other problems, say with this also, then if I introduce this also, then probably I have nothing. Okay, you need to solve a number of problems. Probably Professor Vinayak Pipin will help you to discuss the remaining problems of this topic. Okay, the question paper problems you can solve, because it is only a mechanical thing what you need to do it, and every problem will take about half an hour, and I can't spare so much time only on doing that, and therefore I shall try to wind up the topic of discussion probably today, or if not, at the most I shall take maybe one more session on this, and then I shall wind it up. Okay, so I intend to solve one problem what is called as what is this bill? The cantilever. So cantilever subjected to three types of loads: one moment 100 kilonewton meter, then 30 kilonewton point force. Then I have what is called as uniformly varying load. Okay, 25 kilonewton per meter. This 25 kilonewton per meter is the equation of this line. This is the equation of this line. That means the load here is 0. If you go 1 meter along this, the load will be 25 kilonewton. If you go another 1 meter, then it becomes 50. So only up to here. If it continues, then if you go 1 more meter, then 75, like that. So the load is increasing at a rate of 25 kilonewton for every 1 meter. Okay, that is the meaning of that. Okay, so as usual, it's a cantilever. So for cantilever, we need not find the reactions. And therefore, so straight away go for the reference. What reference do you choose? Reference is equal to, say, D. D is the reference. D is the reference what we select. Okay, then what are the portions you need to identify? Okay, so portions are, what are the portions? Maybe AB, it is the, let me start from the reference, say DC, then maybe CB, then maybe BA. These are the portions what you need to analyze. Okay, probably I can start with what we call as the portion number 1, portion DC. Okay, what you have to do? Take a section between D and C. Take a section. Okay, and draw the free body diagram. Okay, this say is D, and this is my C. Please remember, it is not C. C is beyond this, and this is at a distance of what we call as X. And X varies between, so my section has to be always between D and C, and therefore the range of X is between 0 and 2 meters. Okay, how the load varies, it goes like this. So it is 0 here, and it is increasing like this. Okay, uniformly it is increasing. So the straight line, the equation of this line is 25 kilonewton per meter. So first thing what I need to do is, so I know what is the equivalent point load. So that is nothing but the area of the triangle. So therefore, how much is the load at this end I would like to get? How much is the load at this end? This is X. This is 25, and therefore this load is 25 times X. 25 times X. Now let me show the positive where I have taken the section. No? This is the section where I have cut the beam. The material at that section shall produce shear force. Okay, a shear force which is a vertical or in the plane of the this thing. So what is positive shear force? So now what portion I am analyzing, that is very important. Okay, I have cut it here. Say somewhere here I have cut it. Now which portion I have taken? I have taken the right hand side portion. And for this side convention, the shear force is in the upward direction. And if I take it in the left side portion, then the downward force is the positive shear force. And this is my positive shear force. And this is my positive bending moment, Mx. Okay, once you do that is sufficient. Okay, now let me start the expression for Vx. So I start with Vx, upwards positive. Okay, then I have downward force. This triangular force is a downward force, therefore it is minus. It is minus. Okay, how much? The area of the triangle will give you what is the equivalent force. That is area of the triangle, as I know that half base into height. Half base. Base is what? X. And what is the height? The height is this. That's now what? 25x. Half into x into 25x. Okay, so that's all. Any other force? No. That is equal to 0. Therefore, Vx is equal to not minus, it is plus 25 into x square divided by. So what it means? Immediate observation. Shear force is not constant. Shear force varies. Shear force varies as per a curve. It is a curve. The shear force variation between D and C is a curve. It's a curve. Okay, let me get the shear force at 3 points. One is D, the other one is at C, then the other one in between. That is when x is equal to say 1 meter. That time I shall find out. So for D, x is 0, therefore shear force is 0. For C, x is equal to 2, therefore this is 25 into 2 divided by 2 square. So this is 25, 4 divided by 2. This is equal to 50 kilonewton. And what is the shear force at x equal to 1? This is 25 divided by 2 into 1 square. This is equal to 12.5 kilonewton. So therefore, I can draw what is the variation of the shear force. The shear force at D equal to 0. The shear force at C is 50 plus 50. So this is 50 kilonewton. And somewhere in between, at the midpoint. So its value is 12.5. 12.5 is 1/4 of 50. So whatever the length you have draw that 1/4 of it. And therefore, how is the curve? How is the variation? It varies like this. So this is the variation of the shear force or shear force diagram for the portion what is called as DC. Now let me start for bending moment. So for bending moment diagram, I shall draw one more diagram what is called as, I shall replace this UVL in terms of what is called as a point load. It's only for that purpose. Please remember, so this is X. Okay, so now this is where you have like this height and this. Okay, so now what is the load? The force. The force, equivalent force, that is point force, which will be acting at the center of gravity of the triangle. Center of gravity of the triangle, do you agree that it is closer to this? It is increasing. If I call this distance, it is closer to this. Therefore, it is somewhere here. So this portion is more and this portion is less. And this distance is how much? And this distance is how much? And I know that if your x is the total length of this height of the triangle, if you call this as base and this height, then one is 1/3 edge, the other one is 2/3 edge. So how much is this? This is a 2/3 times x, and this distance is 1/3 times x. So how much is this load? How much is this load? That is nothing but half into x into 25x. This is the load. So this distance is 1/3 x. And I am taking bending moment about this section. Please important. This is very important. Okay? Write down the expression now. This is mx. Okay? Now mx, vx will not have any moment because it is at that section only. Then you have this force, that is nothing but, is it positive or negative? The load is downwards and about this section it has the same sense, therefore it is plus. What is the force? The force is 25x square by 2. 25x square divided by 2. Please remember this is force. Multiplied by what is the distance? The distance is this distance. How much is that? 1/3 times x. 1/3 times x. This is equal to 0. There is no other force. So therefore this is equal to, bending moment is equal to minus 25 divided by 6. 2 into 3, 6. It is x cube. So bending moment is minus 25 by x, 6 into x cube. What is your observation? Bending moment is not constant. Bending moment varies. Bending moment varies as a curve. It is not a straight line. So if it is a curve, then get the 3 points. Bending moment at D. Bending moment at C. Bending moment at some other point where x is equal to 1 meter. Because the length of the portion is 2 meters. I am taking the midpoint. So if x is 0, the bending moment is 0. If x is 2 meters C, that is minus 25 divided by 6 into x is 2. 2 cube. 2 cube is 8. So 25 into 8 is 200. 200 divided by 6. That is nothing but minus 100 divided by 3. So many kilonewton meter. So what is the bending moment at x equal to 1? That is minus 25 by 6. As it is, x is 1 cube. So this is nothing but minus 25 divided by 6. So many kilonewton meter. It is as good as 12.5 divided by 3. If I want to compare this value and this value to have the same denominator, I can write it as minus 12.5 divided by 3. Just for the sake of comparing it. So this is 100 and this is 12.5. That is almost 1/8. Whatever the length you draw to represent this, its 1/8 portion is this. Okay, let me come back here. What I mean by that, I shall explain. The bending moment at B is equal to 0. Bending moment at C is minus 100 divided by 3. This is 100 divided by 3. And at the midpoint, okay, how much is that? It is minus 12.5 divided by 3. So 1/8. So this is half. And half of this is 1/4. Half of this is 1/8. It is so small value. So draw that drawing by means of a curve, smooth curve, and this is how it does look. Okay, this is what is the bending moment diagram for the portion DC. Now let me go to the next portion, what is called as CD. The portion CB, okay, take a section between C and B and draw what is called as the free body diagram. So this is your D, say, this is somewhere here is your C, and please remember this is not B, this is where I have taken section, and from here to here, this distance is, what is x? And I know that this is 2 meters, and therefore this distance is x minus 2. Okay, so now I have what is called as a uniformly varying load. This is 25 kilonewton per meter. Okay, any other load? I don't have any load. So the loads will appear again only from B onwards. So therefore, I shall show you what is my positive shear force and what is my positive bending moment. So shear force diagram, okay, shear force, let me start with Dx upwards positive. So the only other force what I have is this UVL, which is in the downward direction, therefore it is minus. And how much is the force? It is nothing but the area of the triangle, that is half into base. If you call this as base into 2. And what is the height? Please remember what is the height. So that is this value. How much is this value? So this is, here the load is 0. If you go 1 meter, the load is 25. If you go 1 more meter, then the load is 50. That means this load is 50 kilonewton. So therefore this into 50. So this is force what we are talking. This is equal to 0. So 2 cancels, and therefore Dx is equal to 50 kilonewton. The shear force between C and B is constant and it is equal to 50 kilonewton. So therefore you can straight away draw this. Shear force is equal to 50 kilonewton. Okay, so now what is the bending moment diagram? Bending moment for this portion, bending moment. I shall replace. Okay, this is my diagram, this is my D, this is C. Okay, so this is where the section is. This is what is X. And this I know that it is 2 meters. Okay, so I have load something like this. This I would like to replace it by a point load. I know that the point load is going to be closer to this height. Okay, okay, how much is that? So this distance is 2 by 3 times what? 2 by 3 into 2, because in place of X that is 2 meters. And how much is this distance? This distance is 1 by 3 times 2. This distance is 2 meters and this distance is 2/3 of 2. That is this. And this distance is 1/3 of 2. Okay. So how much is the force that I have already obtained? That is equal to this. Half into 2 into 50. So half the area, the base say 2 meters, and what is the height? Height is 50. 2 cancels, you have what is 50 kilometers. And the bending moment, this is what is my bending moment, Mx. Okay, we start with Mx. Then the bending moment, because of this, about this section, that also is positive. Okay, how much is the force? The force is 50 kilonewton. What is the distance? It is from here to here. From here to here. So how much is this? This is 2 meters from here to here. This is x minus 2. So x minus 2 plus 1 by 3 into 2. Or in other words, from here to here is x. And I know that this distance, that is nothing but 2 by 3 into 2. That is also equal to x minus 2 by 3 into 2. So this is equal to 0. So therefore, mx is equal to, so minus 50 into bracket x minus 4 by 3. So that means, what does it mean? The bending moment is not constant. Bending moment varies because of the presence of x raised to 1. The bending moment varies linearly. Bending moment varies linearly. Therefore, bending moment at C and bending moment at B, 2 points are sufficient for me. 2 points are sufficient, and therefore, so what is the C at C? I forgot to write this. What is the range of x for the portion CB? It is 2 to 4. The smallest value at C, 2. So minus 50 into 2 minus 4 by 3. So this is equal to minus 50 into 6, 3 to 2, 6 minus 4 divided by 3. Okay, so 6 minus 4, 2 by 3, 2 by 3 into 50. This is minus 100 divided by 3. Bending moment at C is minus 100 by 3, and bending moment at B, substitute x equal to 4. So this is minus 50 into 4 minus 4 by 3. So this is, so 4 minus 4 by 3, this is minus 50 into 12 minus 4 divided by 3. 12 minus 4 is 8. So 8 into 50 is 400. This is minus 400 divided by 3. So therefore, so this is 100, and the 400 divided by 3 is the bending moment. Here it is 4 times this. 4 times this. I don't have that much space, and therefore I shall draw a smaller line and write it as 400 divided by 3, and join it in between and draw what is called a straight line mediation. So moving on to the last portion, that is BA. That is portion BA. Portion BA. What is happening? Okay, portion BA. So draw the free body diagram. Okay. So B. It starts from B. You have C. Then you have B. Okay. A has not been reached yet. And from D to E, this section. This is what is X. Then what are the loads? You have UVL for the portion. This is how it is. And this load is 25 kilonewton per meter. Then at B, you have a point load which is equal to 30 kilonewton. Then at B, you also have a load. This is 100 kilonewton meter. And this is where your section is. This is the section, and we are considering the right hand side portion. So shear force positive is Vx, and this is the bending moment Mx. Okay, so now let me start. So Vx upward positive, proceed further, you come across 30 kilonewton, which is downwards minus 30. And the other one is 100 kilonewton meter, it is a moment, therefore it is not force, leave it, then proceed further. Then you have a load here, which is in the downward direction, therefore it is negative. Then how much is the force? The area of the triangle, half into base. What is base? This is 2 meters, as we know, this is 2 meters, this also is 2 meters. Okay, so this base, and what is this height? As I have shown you earlier, it is 50 kilonewton. This is 25 kilonewton per meter. At that rate, it is increasing at a distance 2 meters. What is this height? This height is 50. So this is equal to 0. So therefore, 3x is equal to 2 and 2. You can see 50. This is minus 30, minus 50, minus 80. Take it to the other side. It becomes 80 kilonewton. The shear force between the portion B and A is 80 kilonewton. It is plus. Okay, so now let me draw. So there is no need to draw separately because it is not varying. So shear force at B is 80 kilonewton. Draw a line and write down the 80 kilonewton. And this is constant. And this also is 80 kilonewton. And whatever this is nothing but the shear force line. Some people, what they do is they hatch like this. So when you hatch, it doesn't matter. I hope it's clear. This is the shear force diagram, and go for bending moment diagram, Mx. Okay, whenever you are writing the expression for Mx, and if your analysis portion indicates or has uniformly distributed load or uniformly varying load, then get the equivalent point load and then write down the expression. Okay, you may draw it separately, or if you can do it mentally, then both things are fine, no problem. But I would like to have it separately. Okay, say this is D, say this is C, say this is D. Okay, only UVL I would like to replace it, and everything else I can refer that diagram. Only UVL. So UVL is closer to this point C, the center of gravity. So how much is this distance? This is 1/3 of 2. And how much is this? This distance is 2/3 of 2. So what will be this distance from here to here? This distance is x minus 2/3 of 2. Okay? So I have not shown the other forces, point force and this thing, for which I can refer to this diagram. So I shall start here, mx, fine, mx, clockwise moment positive, vx, at the same section shall not produce any moment. Then 30 kilonewton, the moment due to 30 kilonewton about this section, that also is clockwise, therefore it is plus 30 multiplied by, what is the distance? This distance. This is x minus 4. This distance is x minus 4. This is x, this is 2, this is 2, therefore x minus 4. 30 into x minus 4. Okay, 30 into x minus 4. Okay, then 100 kilonewton meter. This also is clockwise. This also is clockwise, therefore it is plus and 100 straight away, and not multiplication, nothing. It is not a force, it is already a moment. Then proceed further. For this, we can come back here. Okay, first of all, sign downwards. This is the section. This is also clockwise, therefore this is also plus. So how much? Then how much is the load? First of all, the load is half into 2 into 50. Half into 2 into 50. Half into 2 into 50. This is the base. Half base height. Okay, multiplied by the distance. What is the distance? X minus 4 by 3. This is equal to 0. Okay, so therefore mx is equal to, you have shown me all negative, minus 30 into x minus 4. Then this is minus 100. Then this is 2 cancels, and this is 50 into x minus 4 by 3. All this is what is the expression for mx. Observe it carefully. We have x on the right hand side, therefore it is not constant. So, but we have x raised to 1 only and x raised to 1 here. Therefore, the bending moment varies linearly. So, therefore, bending moment, what is that? Portion B, and bending moment at A. Only two portion, but I should have written this at the beginning. Then the range of x is between 4 meters and 6 meters. So, therefore, for portion B, x is 4 meters. 4 meters. The first term is not there. 30 into minus 30 into 4 minus 40. Then minus 100 minus 50 into 4 minus 4 by 3. 4 minus 4 by 3 is 8 by 3. 4 minus 4 by 3. 4 by 4. I can write it as 12 by 3. 12 by 3 minus 4 by 3. 8 by 3. So this is, okay. So this is 400 by 3. This one, and 300 by 3. This is minus 700 by 3 kilonewton meter. And similarly, the bending moment at A, so for that I have to substitute x equal to 6. 6 minus 4, 2 into 30. This is minus 60. This is minus 100 as it is. Then minus 50 into 6 minus 4 by 3. 6 I shall write it as 18 by 3. So 18 by 3 minus 4 by 3 is 14 by 3. 14 by 3. 14 by 3. 14 by 3. So this on simplification, this is 3. Okay, this is minus 180. So this is minus 300 and 15 to 14. 15 to 14. 140, 145 into 5. This is 700. Okay, 700, 300, 1000. 1000, of course, minus 1080. Sorry, not 1000. 1180. 700, 300, 1000, 100, 1180 divided by 3. And if it is simplified, 5. Otherwise, also we can write it as it is. Okay. So this is the bending moment at B is minus 700 by 3. Okay. So if you want me to change this diagram, okay. Otherwise, what I shall go here is go below this. Go below somewhere here. This up to here, and probably here this value is still more, and anything like this. I hope you are able to draw it. I haven't drawn. Okay, it is going beyond this thing. Okay, I don't have even small space, a small thing here, and write down what is the value there, and here also, and that is how the bending moment and shear force diagram. So even whether it is UVL or UDL, whatever may be the load, if more the portions of the beam, then it will take more time. But there is nothing like difficult or anything. It will test your patience, and therefore please exhibit lot of patience so that you will not commit any mistake. The last topic what I intend to discuss in this, so maybe if you refer books for this topic, the derivation what I intend to do now, probably you will find it in the beginning of the topic itself. And what is called as, what is the relationship between the bending moment, shear force, because the material at the section that itself will produce what is called as shear force, the same material is producing bending moment also. Therefore, there must be some relationship between the bending moment and shear force. So therefore, what is that? Suppose you have a beam, okay, you have a beam, and say this is subjected to, so whatever may be the load like this, it is not only uniformly varying, it is varying, and let the equation for this is what we call as W of X. That means this W, this is W, this is W, and this W is varying. So that's why I call it as W of X. So this is W of X. Okay. So now I have some reaction. Here also I have some reaction. Now what I do is I cut this beam at a section. Please remember, this is my beam. This is beam. This is what is load. The relationship what I am doing is relationship between load, shear force and bending moment. This is what I intend to do. Okay? So now, so I have load like this everywhere. I have load in the entire. I have made it a very, very general case. So what I am going to do is, so this is where I take a section here. Okay, I am not happy. So say probably I shall take the left hand side portion only. So this is where the section is, and this is where you have the load is. Okay. So this is at a distance X. And now I am going to cut one more section. And this is the portion of the beam. What I intend to analyze, what is the distance of this? This will be a small portion. So I am going to consider a small portion here. Okay? But for the sake of analysis, the length is so small, probably your naked eyes may not be able to visualize it. But for your clarity, I shall draw it as if it is a bigger one. Please remember, this is my dx. So where all I have cut it, I have cut it both ends. I have cut it here. And I have cut it here also. Please remember, I have cut it at both ends. Okay, so at this section, the section is to the what? The portion of the beam is towards the right side. Therefore, what is my positive shear force? My positive shear force is upwards. I have taken section. Where is the beam portion? The beam portion is to the right side. And what is my positive shear force? It is Vx. And what is my positive bending moment? It is Mx. Okay, now let me come this side. So I have taken section. How is your positive shear force, or how is where is the portion of the beam? It is left side. What is my positive shear force? It is downwards. It is positive. And what is the positive bending moment? This is my positive bending moment. Okay, so I cannot call this also as Vx if I say that this magnitude and this magnitude are one and the same. I presume in general that the bending moment, shear force vary with length. Okay, my reference is somewhere here. I have taken one section and this is another section. So therefore, I shall assume that it is a little more than this. I shall call it as dVx multiplied by plus dVx. The shear force here is Vx plus dVx. dVx is a small increment with respect to this. And similarly, the bending moment also I shall take that it is Mx. It is not just Mx, it is little more than that, dMx. So in a special situation, this dMx may be 0. The bending moment here is also equal to this. The shear force also equal to this. That may be a case. I shall assume that they are varying. Okay, these are the things. Then what about the load here? What about the load? I can assume that the load is constant. How can I assume? It is varying, I know. I have shown the diagram like this and I am writing as if it is a constant here. How can I justify this? This I can justify this because dx is very small. When I say that dx is very small, the load on this side and the load on this side, and in between they are one and the same. And this is what I call it as W, uniformly distributed load. So how can I justify uniformly distributed load? Because the portion of the beam what I am talking is very small, that the load throughout this length is constant. Okay, so do you agree that this portion, this along with this bending moment forces, all this is in equilibrium state? Yes, it has to be. A beam which is in equilibrium state, then any portion of it also must remain in equilibrium state. That is the basis on which we are studying our mechanics of materials. So therefore, apply equilibrium conditions. Let me apply equilibrium conditions. Start from here. Okay, this is say Vx. I shall start Vx. Okay, so this is Mx anyway. Then this load, it is downwards, therefore it is minus. Okay, into W multiplied by what? W into dx. That is the load. Okay, then further you see this is downwards. This is minus Vx plus dVx. Okay, or this is bending moment. This is equal to 0. Okay, so therefore simplify Vx minus W dx minus Vx minus dVx is equal to 0. So this Vx and this Vx we cancel. Okay, so this W dx I shall send it to the other side, or this dVx anyway. This minus W into dx is equal to dVx. Send this dx also this side. Then what is that? Minus W is equal to dVx divided by dx. Or you can rewrite it the other way. Okay? Or you can write it as W is equal to minus of dVx divided by dx. This also is okay, both of them. That means the load at a section is the rate of change of shear force with respect to the length. So this is what we call it as the relationship between the load and shear force. Load and shear force. Okay. This, when I apply the equilibrium condition for forces, then this is what I get. Then if you take moment now, then if you take the moment, one button. Airplane mode. I wish to continue and the relationship between bending moment and this thing. Okay, I shall take moment about some section. So any section. Okay, let me say I shall take moment about the left hand side section, that is equal to mx, fine. Okay, vx will not have. Then this w. Okay, and it is in the same direction, therefore it is plus w into dx. This is the force. W into dx is the force, and multiplied by the distance, that is nothing but dx by 2. Then this v plus vx, that also produces moment. Please remember, I am taking the moment about the left hand side. This is the force here, vx plus dvx multiplied by into dx. It is in the same sense as that, this mx. Then minus mx, minus of mx plus dmx. This is equal to 0. Okay, so now simplify this. Okay, so first of all I can remove this bracket here, so I can cancel this mx and this mx. Okay, then so dvx into dx. So first of all, this w into dx, w into dx raised to 2. dx as it is very small and it raised to 2, it is still 0. So therefore this can be neglected. Then you are left with this. So I shall simplify this. This is vx into dx. Then I have dvx into dx. Again, this is too small. dvx into dx. The product of two infinitesimally small quantities can be neglected. Then minus this minus. Okay, this minus. When I have minus and here minus. This is equal to dmx. This is equal to 0. So therefore, take this. Vx is equal to dmx divided by dx. So the rate of change of bending moment is equal to the shear force. So this is the relationship between shear force and bending moment. Okay, all the best. With this I conclude this topic, and when we meet we shall discuss a new topic.